Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Okay, this is my third lecture of the lecture series on algebraic graphs. As you know, in the previous of my two lectures, I introduced some noun groups, and then in the second lecture I have given some probabilities associated to a group. First of all, let me just remind you about my rearrange my lecture in three parts. As I mentioned in the first lecture, I put in as part 1. In the first lecture on 17th of April, I introduced some noun groups. In the second lecture on 24th of April, I introduced some probabilities associated to a group, and this is my third lecture today, and I would like to talk about some noun algebraic graphs. So part 1 is devoted to groups, probability, and graphs. In the second part, I put 2 lectures about the spectral graph theory in general and in particular for algebraic graphs. So next week and the week after that, I will talk about spectral graph theory as the second part of my talk. And in the third part, the last part of my talk in this series include 2 lectures on the 2nd of July and 16th of July. I will mention about some topological indexes in algebraic graph. So this is the outline of this series of lectures, and I will follow this arrangement for my talk. Okay. Now, what I would like to mention today is to introduce some noun algebraic graphs. As I mentioned in the first part of my lecture on 17th of April, you know, we are going to combine algebraic structures and graphs. So algebraic graphs is a combination of 2 concepts, graph and algebra. And today I will introduce some important algebraic graphs, and also I will combine probability, which I mentioned in the previous lecture, and some relations between probabilities and algebraic graphs. So today I will introduce some important graphs mostly associated to groups, but I will also introduce two algebraic graphs associated to a ring. Anyway, let me just start introducing algebraic graphs. Now, the first graph which I'm going to introduce is commuting and non-commuting graph associated to a group. So let us define the commuting and non-commuting graph. First, we introduce non-commuting graph. Suppose that G is a finite group and Z of G is the center. Center means the set of all elements of G such that they are commute with all other elements in the group. So the non-commuting graph of a given group G, which we may denote by gamma G, is an undirected simple graph, so there is no direction, and also it's simple graph. Simple graph means that we don't have any loop, right? And the vertex set of non-commuting graph consists of all non-central elements. Non-central elements means the set of G minus the center. So we have to just move. We have to move the center from the set of elements of G. So G minus the center is the vertex set, and two vertices X and Y, they will we will have an edge between them if and only if X and Y are not commute, which means XY not equal to YX. So we say non-commuting graph for a given group G. Let me just I give a note at the beginning of my talk here. You know, what you have to know is you have to have a little bit background on graph theory. So I'm not going to define graph and just some basic properties of graph and many kinds of graphs. So you may just read some graph theory book and just see some definitions about important concepts of graph theory. So we don't have time to give a background on graph theory. So the non-commuting graph is a graph associated to a group G, right? And you know, we always assume that G is a finite group. Of course, we may assume that G is infinite, and the definition is still true. But because we are going to draw a graph and just draw edges, so we assume that the group G is finite. So the vertex set is G minus the center, and two elements x and y are adjacent if and only if xy not equal to yx. Now, the complement of non-commuting graph is commuting graph. So the commuting graph, we have the same vertex set. So the vertex set is again G minus the center. So that's all non-central elements of G. And two vertices x and y are adjacent if and only if x and y commute. xy is equal to yx. So that's the commuting graph, which is the complement of non-commuting graph. Now, let us give some examples. Consider the symmetric group S3. We have 6 elements here, right? Identity, we have 3 transpositions, 1, 2, 1, 3, 2, 3. And 1, 2, 3, 1, 3, 2. And we know that the center of symmetric group of order 6 is trivial. So if we are going to draw the non-commuting graph, first we have to determine the vertex set. So the vertex set is set of all non-central elements. So we have to move the center from the set of elements of G, since the only identity elements is in the center. So if we move identity from the set of elements of S3, so the vertex set consists of 5 elements. We have 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. Right? Now, here is a graph. You can see that 1, 2, for example, is adjacent to 1, 3. Why? Because 1, 2 times 1, 3 is not equal to 1, 3 times 1, 2. In other words, 1, 2 and 1, 3 are not commute. So since 1, 2 and 1, 3 are not commute, then we will have an edge between 1, 2 and 1, 3. But here you can see we don't have edge between 1, 3, 2 and 1, 2, 3, because you can see that 1, 3, 2 is the inverse of 1, 2, 3. So 1, 2, 3 times 1, 3, 2 is identity. And you know it's equal to 1, 3, 2 times 1, 2, 3. So 1, 2, 3 and 1, 3, 2 are commute. And by this reason, we don't have edge between 1, 2, 3 and 1, 3, 2. So here is a graph, and you can see that we have 9 edges here. Just you may consider the complete graph K5 and remove 1 edge, right? Now, how about the commuting graph of S3, which is the complement of the non-commuting graph? So here, as you can see, we will edge between any of 2 vertices except 1, 2, 3 and 1, 3, 2. Now, for the complement of non-commuting graph, here we have only 1 edge between 1, 2, 3 and 1, 3, 2. So the commuting graph of S3, we have 3 isolated vertices and 1 edge. So we will have only 1 edge here. Now, let us give a relation between commutativity degree, which I define in the second lecture about probabilities. You know, one of the probabilities which I define once the commutativity degree. Now I'm going to give a relation between commutativity degree and commuting and non-commuting graph. Now, here is the commutativity degree. You can see the commutativity degree, which was denoted by d of g, is the set of all pairs x and y which are commute divided by order of g square. Now, if we put two sets A and B, put A set of all pairs x and y such that x and y are commute, and B is the set of all pairs which are not commute. So if you consider the Cartesian product of G by G, so the set of all pairs in G can be split in two disjoint sets, set of xy such that xy is equal to yx, and the set of all pairs xy such that xy are not equal to yx. Now, you can see that the Cartesian product, the G cross G, is the union of A and B. So order of G square, right? So order of G cross G is order of G square, is order of A plus order of B, because we don't have any intersection between A and B. So you know that the commutativity degree is the set of all commuting pairs, which is A. A is the set of all commuting pairs. So the commutativity degree is the set of the size of the order of A, size of A divided by order of G square. So here you can see that. So order of A here is equal to order of G square times d of G. Now, how about B? You can see that B is the set of all pairs x and y such that x and y are not commute. You know here, because xy is not equal to yx, so x and y are vertices here because they are not in the center, and also we will have an edge between x and y. But here you can see x, we have order pairs, so the order pair x and y is different to the order pair y and x. But for both of them we have only one edge. So the size of B is 2 times of the number of edges of the graph. So if we combine the equation 1 and 2, you can see that so order of G square is order of A plus order of B, which is equal to order of G square times the commutativity degree of G, plus we can put for the size of B is 2 times the number of edges. So the number of edges can be obtained by this formula. So the number of edges is half of order of G square times 1 minus d of G. Now, you can see by this formula, if we have the commutativity degree, right, then we can find the number of edges of non-commuting graph. And conversely, if we have the number of edges by this formula, we can find the commutativity degree. Or if we have a lower bound for the commutativity degree for d of G, then we can get a lower bound for the number of edges. And similarly, if we have a lower bound for the commutativity degree, we can find an upper bound for the number of edges. Right. Let me just give a generalization of a non-commuting graph. You know, for the non-commuting graph, I define the vertex set is the non-central elements is G minus the center, and we will have H between X and Y if X and Y are not commute. Now here we are going to just consider a fixed subgroup H of G, and we are going to define relative non-commuting graph of a subgroup H of G. Let us define the relative non-commuting graph. Suppose that G is a finite group and H is a subgroup of G. The relative non-commuting graph of subgroup H of G, we may denote it by gamma H. G is again undirected simple graph, and the vertex set is G minus the centralizer of H in G. You know, the centralizer H of G is the set of all elements of G such that these elements commute with all elements in H, right? So G minus the centralizer of H in G is the vertex set, and two vertices X and Y are adjacent if and only if we should have two conditions. The first condition is that X and Y are not commute, so XY not equal to YX, and the second condition is that one of vertices X and Y must be in H, right? So we can see that, as I mentioned, the vertex set is G minus the centralizer of H in G, and this is the definition of the centralizer of subgroup H in G, which is the set of all elements G in G such that H is equal to HG, so G commute with H for all element H in H, and X is adjacent to Y if and only if, so we should have two conditions. The first condition is that X and Y are not commute, and one of X or Y must be in H. Now let me give example. Again, we consider the symmetric group S3, so we have 6 vertices here, right? 6 elements here, and we assume that H and K are 2 subgroups of order 2 and 3 respectively. So H consists of 2 elements, identity and transposition 1, 2, and the subgroup K consists of 3 elements, identity, just cycle of length 3, 1, 2, 3, and 1, 3, 2. Now, we can see that the centralizer of H in S3 is equal to H. So the only identity and 1, 2 are elements which are commute with all elements in H, not anymore. And similarly, the centralizer of K in S3 again is K. So if we if we put the vertex set for the relative non-commuting graph of H in G is S3 minus the centralizer of H in S3. So here is S3 minus H. Now you can see that we have 6 elements in S3, right? And we have 2 elements in H, so we will have 4 elements as a vertex set of H in G. So you can see that these 4 elements are outside of H. So in spite of the fact that 1, 3 and 2, 3 are not commute, but because 1, 3 and 2, 3 are not because if we have an H between 1, 2 and 1, 3, we should have at least one of 1, 3 or 2, 3 in H. But 1, 3 and 2, 3 are not in H. So we don't have any H between 1, 2 and 2, 3. And similarly, we don't have any H between 1, 3, 1, 2, 3, 2, 3, 1, 2, 3, and 2, 3, 1, 3, 2, and so on. So we have 4 isolated vertices here. For subgroup K, we have also the same structure. So subgroup K has 3 elements, and the centralizer of K in S3 is equal to K. So the vertex set of the relative non-commuting graph of H in S3 consists of 3 elements, 1, 2, 1, 3, and 2, 3. But as you know, 1, 2, 1, 3, 2, 3 are not in K. So here we have again 3 isolated vertices here. So let me give a note here. If H is an abelian subgroup, so if H is an abelian subgroup, so obviously H is contained in the centralizer of H in G. So in this case, we don't have, all, because the vertex set is G minus the centralizer of H in G. So if H is an abelian, so all vertices in the vertex set are outside of H. So here in this case we don't have any H, and so what we have is only some isolated vertices. Now I introduced the relative non-commuting graph, now similar as to the relation between commutativity degree and number of edges in non-commuting graph. We will have a relation between relative commutativity degree and the number of edges of relative non-commuting graph. Suppose that G is a finite group and H is a subgroup of G. Now we can see that the number of edges of relative non-commuting graph H in G is equal to the multiplication of order of H and order of G times 1 minus the relative commutativity degree of H in G minus order of H square over 2 times 1 minus the commutativity degree of H. The main point is that if in the relative commutativity degree, if we put H as a whole graph, a whole group, because we know that one of subgroups of G is G itself. So if H is in G, then we will get the usual non-commuting graph gamma G. So here is the number of edges of relative non-commuting graph in terms of the relative commutativity degree, which I introduced in the previous of my talk, and also the commutativity degree of subgroup H. You know that we in the relative non-commuting graph, we always assume that H is non-abelian, because if H is abelian, then as I mentioned before, we will have only some isolated vertices, so the number of edges is 0. I don't actually have more time to deal with each graph and state many properties and many problems related to this graph. I just want to introduce as a bit of description for just some non-algebraic graphs. So the first graph which I introduced, commuting and non-commuting graph, and the second one is the relative non-commuting graph. Now I'm going to define the third algebraic graph related to a group, which is co-prime graph. You remember I defined co-prime degree as one of the probability. So suppose that G is a finite group. The co-prime graph of G, we may denote by gamma co-prime of G, is a graph which is undirected simple graph. The vertex set is all elements of G, and two vertices X and Y are adjacent if the order of X and order of Y are co-prime. Right? It's a little bit similar to the co-prime degree. As an easy example, if you look at symmetric group S3, right? We have 6 elements here, so you know the order of these six elements. Identity has order 1, 1, 2, 1, 3, and 2, 3. They have order 2, and 1, 2, 3, and 1, 3, 2. They have order 3. So we have 6 elements, so we have 6 vertices here. Now, as you know, identity has order 1, so you know that 1 with any other integers are coprime. So identity is adjacent to all other vertices here. Now look at 1, 2. 1, 2 has order 2, and we don't have edge between 1, 2 and 1, 3 because the greatest common divisor of 1, 2 and 1, 3 is 2. But 1, 2 and 1, 3, 2, they have coprime order because 1, 2 has order 2, but 1, 3, 2 has order 3, and 2 and 3 are coprime. So here, 1, 2 is adjacent to 1, 3, 2, 1, 2, 3, and similarly 1, 3 is adjacent to 1, 3, 2, 1, 2, 3, and 2, 3 is adjacent to 1, 3, 2, and 1, 2, 3. So we have 11 edges here. Now let me give another example for a dihedral group of order 10. So D10 is a group generated by A and B. A has order 5, B has order 2, and we have a relation BAB is A inverse. So we have 10 elements here. Identity A square, A cube, A to the 4, B, AB, A square, B, A cube, B, and A to the 4B. Look at the order of elements. Identity has order 1. So A square, A cube, A to the 4, they have order 5. B, AB, A square B, A cube B, and A to the 4B, they have order 2. So you know that identity is adjacent to all elements, all elements of D10, right? We don't have any edge between elements of order 5, so A is not adjacent to A square because both they have order 5. But similarly for order 2, we don't have any edge between elements of order 2, but any elements of order 5 is adjacent to any elements of order 2 because 2 and 5 are coprime. Here is the coprime graph. We will have 29 edges here. Now let us give a relation between coprime degree and coprime graph. So this is the definition of coprime degree. Coprime degree is the set of all pairs x and y such that x and y are coprime order divided by order of G square. Now by this definition, so the order of G square times the coprime degree is the size of the set of x and y, which x and y are coprime. Now we can split this set into two disjoint set, the set of pairs x and y, which x and y are coprime order, and x is not equal to y, union to the set of all pairs x and y such that x and y are coprime order and x is equal to y, right? So the first set, the size of the first set is twice of the number of edges of coprime graph, and the second set has only just one pair, identity and identity, right? So we will get the formula for the number of edges of coprime graph. So the number of edges of coprime graph is the half of order of G squared times the coprime graph minus 1. For example, if you look dihedral group of order 8, we have found, we have already defined the coprime degree of D8, dihedral group of order 8, is 15 over 64. Now, by this amount, we can find the number of edges for coprime degree of D8, and as you can see, the number of edges is 7. And similarly for S3, we have the number of edges is 11, and also for Z4, which here we have 3 edges. Now by this amount and D10, right? So we can find the coprime degree for each of them. So if we have the number of edges, we can find the coprime degree, and conversely, if we have the exact amount of coprime degree, then we can compute the number of edges. All right, now let us move to another algebraic graph, which is conjugate graph of a group. You know the definition of two conjugate elements. If we have a group G, so two elements X and Y, we have X and Y are conjugate if and only if there exists an element G such that X to the G is Y. Now by this definition, we can define the conjugate graph. So the conjugate graph, the vertex set is the set of all elements of G, right? So that's the vertex set. We denote the conjugate graph by gamma C of G. And two elements X and Y are adjacent if and only if there exists an element G in G such that X to the G is Y. X to the G means G inverse XG. So X to the G is Y is equal to say that X and Y are conjugate. So by this reason, we denote this graph as conjugate graph. For example, again, if you see the symmetric group S3, we have 6 elements, right? The conjugate graph has 3 components, right? Connected components. So we have isolated vertices as identity, because identity is conjugate to only itself. So we have a triangle. So you know we have 3 vertices, 1, 2, 1, 3, and 2, 3. These 3 elements are conjugate. And also 1, 2, 3, and 1, 3, 2. We have also an edge between them. In other words, if you see the conjugacy class of S3, you can see that we have a singleton set identity, right? So this is the one conjugacy class, and the second conjugacy class is conjugacy class of elements 1, 2, consists of 3 elements 1, 2, 1, 3, 2, 3, and the conjugacy class of 1, 2, 3 consists of 2 elements 1, 2, 3, and 1, 3, 2. So we have 3 distinct conjugacy classes, and the size of each conjugacy class, the first one is 1, the second conjugacy class of 1, 2 is 3. We have 3 elements, and for 1, 2, 3 we have 2 elements. Now if you compare the size of conjugacy classes compared to the conjugate graph, we have a singleton set For the identity, conjugacy class consists of identity. Here we have one isolated vertex. We have 3 elements in the conjugacy class of 1, 2. So we have complement. We have complete graph K3 here, and we have a conjugacy class of size 2. Now we have here K2. So if you look the dihedral group of order A, again we have 5 conjugacy classes here. So conjugacy class of identity, which consists the singleton set identity, right? The conjugacy class of elements A consists of A and A cube. We have 2 elements in the second conjugacy class. The third conjugacy class for A square is only singleton set because A square is in the center, right? And conjugacy class of B consists of B and A square B, and conjugacy class of AB consists of AB and A cube B. So we have 5 conjugacy classes, 2 conjugacy class of size 1 for identity and A square. So here we have 2 isolated vertices and 3 conjugacy class of size 2, right? And here we have 3 edges. So we may denote the above conjugate graph. Now we have 2 isolated vertices, so we may denote by 2K2, and we have 3 edges, 3K2, so this is the union of 2K1 and 3K2. Okay. We may just give a structure for the conjugate graph in terms of the size of conjugacy classes as the following. So suppose that G is a finite group, and if we have K distinct conjugacy classes, conjugacy class of x1, x2, and xk of size m1, m2, and mk respectively, right? Then the structure of conjugate graph is the disjoint union of complete graphs km1, the complete graph of size of order m1, complete graph of order m2, and complete graph of order mk. Right? That's the union of some complete graphs. Here are some basic results about the conjugate graph I listed here, right? So if G is a finite group, and if we have K distinct conjugacy classes of size m1, m2, and mk respectively, then the conjugate degree, we have the formula for the conjugate degree in terms of the size of conjugacy classes. You know, this is order of size of conjugacy graph of xi square, because if you take any conjugacy class, all elements in a conjugacy class are conjugate. So here is the number of edges of conjugate graph, right? So the chromatic number chromatic number, that's the vertex coloring for conjugate graph, is the maximum size of conjugacy classes M1, M2, and MK. The independence number means the biggest size of independent set. Independent set means a set which we don't have any edge between of vertices in this set, right? And we have dominating number. Dominating number is the number of conjugacy classes here. Dominating number means that the minimum size of dominating set, and dominating set is the subset of vertices, right? Which for any vertex outside of this set, we have a vertex, at least a vertex in the dominating set which adjacent to that one. And you can see that. So as I told you, if the size of each conjugacy class is at least 3, then the guess is the minimum size of conjugacy class. So the relation between conjugate graph and conjugate degree is the following. This is the definition of conjugate graph, right? Conjugate graph is the number of pairs x and y such that x and y are conjugate divided by order of g square. Now we can find the relation between the number of edges of conjugate graph in terms of the conjugate degree. So the number of edges is the half of order of g times order of g times conjugate degree minus 1. For example, we have already found the conjugate degree of S3, which was 14/36. Now here, if we use this formula to find the number of edges for the conjugate graph is 4, and you know that for S3 the conjugate for S3, here is the conjugate graph of S3. You know we have 4 edges here, triangle and edge. Here is a simple lemma that states if G is an abelian group, then the conjugate graph is null graph. It means that we don't have any edge, because if the group G is abelian, so each conjugacy class is a singleton set. So we don't have any edge between them. So the number of edges is 0. So as a remark, if we have n conjugacy class for a given group G, which K conjugacy class contains elements in the center and n minus k elements of non-central elements, and you can see that if we have xi is in the center, then the size of if xi in the center, the size of conjugacy class is 1. But if xi is not in the center, so the size of conjugacy class is at least 2. So if xi is not in the center for I between k plus 1 and n, and they have of size mi, then we can see that the graph structure for this group, we have k isolated vertices, and we have the union of n minus k complete graph. Another example for dihedral group of order 12. For dihedral group of order 12, here is conjugacy class of D12. You know, we have two conjugacy classes as a singleton set, because the center consists of identity and AQ. So we have two conjugacy class of size 1 and two conjugacy class of size 2, and another two conjugacy class of size 3. So we have K is 2 because two elements in the center. We have N is 6, that's the order of A, and if we put in the formula, you can find the conjugate degree, and you know that this is the conjugate graph of dihedral group of order 12. We have two isolated vertices, we have two edges and two triangle, and we have 8 edges here. Now let me move to another graph which is called non-normal graph. This graph is a bipartite graph. Bipartite graph means we have a graph consists of two parts. Each part we don't have any edge in each part, or equivalently we have two independent sets, and any edge must be one ends in the first set and another ends in the second set. This called a bipartite graph. Now suppose that G is a finite group and H is a subgroup of G. We define two sets A and B as the following. A is H minus HG. HG is the core of H in G, and that's the intersection of all conjugate subgroup of H. So HG is the core of H in G, is the intersection of H to the G, that's all conjugate of H for any G in G. The set B is defined as G minus the normalizer of H in G. The normalizer of H in G is the set of all elements G in G such that H to the G is H. H to the G means G inverse HG. Right, so we know that we have always H is contained in the normalizer, and HG is contained in H, right? The non-normal graph of H in G we may denote by gamma HG, which is a bipartite graph. So the vertex set consists of the above two disjoint sets A and B. So the union of A and B is the vertex set. And if we have two vertices, H in A and G in B, then we can say that H is adjacent to G if and only if H to the G is not in H. Here you can see easily about non-normal graph. So look at here. So that's all elements of H, right? So HG is a subgroup, is a normal subgroup of H. So we remove HG from H. Here is A, which I colored by green, and here we have all elements of G, and that's the normalizer of H in G, and you know the normalizer consists of H. So we remove the normalizer, and the rest is B, set B, and I colored by blue, right? You can see that there is no intersection between A and B, because A is a subset of H, and here you can see we remove the whole H from B. So this is the non-normal graph. As an example, suppose that S3 we have 6 elements, and look at H is identity and 1, 2 is a non-normal subgroup of S3. So the normalizer of H in S3 is exactly H, and the core of H in G, HS3, is the trivial subgroup. So the set A is H minus HS3. So we remove identity from H, so we will have only 1, 2. And B is S3 minus normalizer of H in S3. So because the normalizer is H, so we remove 2 elements from S3. We will have 4 vertices in B. Now you can see that. So set A consists of only 1 element, 1, 2, and B consists of 4 elements. And you know 1, 2 is adjacent to 1, 3. Why? Because 1, 2 to the, you know, look at the definition. The definition is that H is adjacent to G if and only if H to the G is not in H. So 1, 2 is adjacent to 1, 3 because 1, 2 to the 1, 3 is not in H. So if you compute 1, 2 to the 1, 3, which is 1, 3 inverse 1, 2, 1, 3, is not in H. So we will have an H between 1, 2 and 1, 3, 1, 2 and 2, 3, 1, 2, 1, 2, 3, and 1, 2, 1, 3, 2. So this is a star graph. This is K, 1, 4. And similarly for dihedral group, right? For dihedral group, if we take subgroup H consists of identity and element B of order 2, again we will have K, 1, 4. Here are some results about the non-normal graph. So if H is a normal graph, then we will have no vertices in set A and B. And so since we have no vertices, so obviously we don't have any H. So by this reason we always in non-normal graph, we assume that H is not a normal subgroup. If we compare the size of part A and part B, you can see that the size of part A is less than the size of part B. So the graph has a pendant vertex as if and only if the subgroup H has order 2 and the graph is a star graph. If the size of H is bigger than 2, then the girth is 4, and also we can see that the diameter is at most 4. Diameter is the longest path in a graph. So the diameter is at most 4 and is 2. Diameter is if and only if the graph is complete bipartite graph. If the core of H in G is a maximal subgroup, then the graph is complete bipartite graph. The independence number is the size of the second part, and if H is a non-cyclic group and H minus Hg square is trivial, then the graph is not planar. We can find the relation between normality degree and non-normal graph. The normality degree is the set of all pairs H and G such that H to the G is in H divided by order of H times order of G. Now you can see that we can find the relation between the number of edges and the normality degree. So the number of edges is the multiplication of order of H and order of G times 1 minus the normality degree of H in G. For example, for dihedral group of order 8, the number of edges is 4 because the graph was K14, and you can see that the normality degree by the above formula is 3/4. And similarly for S3, we had K14, the graph structure was K14, and we have 4 edges, and the normality degree is 2/3. We may define the relative non-normal graph. Relative non-normal graph is that we may consider a subgroup H in G, right? And first of all, we may denote the normality degree of subgroup H in K, not if K is the whole group, then this is the normality degree. So if K is a subgroup and H is another subgroup contained in K, this is the relative normality degree, and the relative non-normal graph is the same as non-normal graph, but it's in terms of H, so it's bipartite graph. This subset A is H minus the core of H in K, and B is K minus the normalizer of H in K, right? And two vertices H in A and K in K are adjacent if and only if H to the K is not equal to H. Here are some results. So the relative non-normal graph of H in K is an induced subgraph of the non-normal graph H in K. And if the core of H in K is a maximal subgroup, we will have the complete bipartite graph. The relative non-normal graph is planar if and only if the size of H is at most 11, and if the size of the first part is at least 4, then the graph is not planar. And if H is a subgroup with at least 3 elements, and H is cyclic, then the graph, the relative non-normal graph is outer planar. Okay, now let me define the algebraic graph number 7. Sorry that I have to save my time to define an algebraic graph as much as we can in this lecture. So the one of important algebraic graph which I recently defined and published a paper about this graph is a bipartite graph associated to elements and cosets of subgroups. Let me define the graph. So suppose that G is a finite group, right? We may denote L of G as the set of all subgroups of G. Now the bipartite graph gamma G we define as the following. The vertex set is the union of A and B. A is the whole group, all elements of G, and B is the set of all subgroups of G. Now two vertices X in A and H in B, so elements X as an element in G and subgroup H in G. They are adjacent if and only if the left coset XH is equal to the right coset of H. XH is equal to HX, right? So set A consists of all elements of G, and set B is consists of all subgroups of G. If we take an element X in A and H subgroup H in B, we say that X is adjacent to H if and only if XH equal to HX. So this is the graph associated to elements and subgroups and cosets. For example, suppose that S3 we have 6 elements. Now subgroups of S3 we have 6 subgroups. You know, we have trivial subgroups, we have 2 subgroups of order 2, 3 subgroups of order 2, right? And 1 subgroups of order 3, and the last one is the whole the subgroup consists of all elements of S3. So we have 6 subgroups, so we have 6 vertices in the set B, and we have 6 elements in set A. So we have 6 elements on the left hand side in set A, and we have 6 subgroups in the second part. Now you can see that identity is adjacent to each of 6 vertices in the right hand side, because coset of identity times, for example, H0 is equal to H0E, identity H1 is equal to H1 identity, so identity is adjacent to each of them. Now look at 1, 2. 1, 2 is adjacent to H0 because H0 consists of is a trivial subgroup. 1, 2 is adjacent to H1 because H1 consists of 1, 2, right? If X is in H, so XH is equal to HX. And 1, 2 is adjacent to H4 and H5 because H4 and H5, you know, in the right hand side we have H0, H4 and H5, they are normal subgroups. So because they are normal subgroups, so they will adjacent to all elements of the left hand side. Now here is another example for a cyclic group of order 8. We have 8 elements here. Now subgroups, we have H0 trivial subgroups, H1, H2, H3. So we have 4 subgroups of Z8, cyclic group of order 8, and we have 8 elements of Z8. So the set A consists of 8 elements, and the set B consists of 4 vertices, because we have 4 subgroups. Since Z8 is a cyclic group and is abelian, so all subgroups of Z8 are normal, and so we have complete bipartite graph. Here are some results. If G has at least one non-trivial and proper subgroups, then the graph has no isolated vertex. The graph is always connected, and diameter is at most 4. If the center is not trivial and the set B has at least 2 elements, then the girth is exactly 4. The graph is a complete bipartite graph if the group is Dedekind group. Dedekind group means that all subgroups of the group are normal. So if G is a non-trivial group, then the graph cannot be 3. 3 is a connected graph with no cycle. If the dominating number is 2, if G is a cyclic group of order prime number, then the graph is planar. If G is a cyclic group of order PQ, which P and Q are 2 distinct prime numbers, then the graph is not planar. And similarly for the cyclic group of order N, we have this condition for the graph to be planar or is not planar. And also if G is a finite group, right? So if G is not simple group means that the only normal subgroups are trivial and the whole subgroup. So if G is not simple, then the graph is not planar. If G is simple and non-abelian, then the graph, if G is simple and abelian, the graph is planar. If G is simple and non-abelian, the graph is not planar. And for the Hamiltonian, we can see that the graph for dihedral group of order 2 times P for prime number P is the graph is Hamiltonian if and only if P is equal to T. And we have some results for the dihedral group of order 2 times P square and P cube. And here is a conjecture that the graph for dihedral group of order 2 times n is Hamiltonian if and only if n is 3. I have checked this for many values of n and it was true, but I have not been able to prove it in general. Here are some research problems, so we can check and determine the Hamiltonian property of this graph for some other kind of groups like generalized quaternion group, semi-dihedral group, projective special linear group, and so on. And the second problem, find the adjacency matrix, eigenvalues, and energy of this graph for some kind of groups. In the next lecture, I will introduce about some matrices associated to a graph like adjacency matrix and so on. So the number 8 of algebraic graph is central graph. Central graph means that if G is a group and ZG is the center, so the central graph we may denote by gamma ZG. The vertex set is the whole elements of G, the whole group, all elements of G, and two elements X and Y are adjacent if and only if the multiplication of X and Y is in the center. So the vertex set is G and X is adjacent to Y if and only if of two distinct elements X and Y. X, Y is in the center. You can see that if X and Y are both in the center, so obviously the X, Y is in the center, right? But the point is that what will happen for other elements outside of the center. We have to note that we don't have any intersection, because if X is adjacent to Y, then Y is again adjacent to X, because you know the center is a normal subgroup. So if X, Y is in the center, then because center is normal, so X inverse X, Y, X is in the center. So it means that Y, X in the center. So we don't have any direction. If G is an abelian group, so G is equal to the whole group, right? And obviously the graph is a complete graph. Now for the symmetric group, we know that the center of symmetric group is trivial, right? Now the graph is the following. You know, we have 4 isolated vertices here, right? And we have one edge between 1, 2, 3 and 1, 3, 2, because here you can see 1, 2, 3 times 1, 3, 2, because 1, 3, 2 is the inverse of 1, 2, 3. So 1, 2, 3 times 1, 3, 2 is identity, and it's in the center. So we have 4 isolated vertices and one edge. Is K4 bar union to K2. For dihedral group of order 8, we can see that we have 4 edges, because the center of D8 consists of 2 elements, identity and A square. So you can see that E times A square is in the center. A times A cubed is A to the 4, which is trivial. Identity is the center and similar. So we have 4 edges. And the same thing we have for the quaternion group. We still have some 4 edges. Here is some results about the non-central graph, right? So we have 3 equivalent proposition. G is abelian group equivalent to the graph. Central graph is complete graph or connected, And if we define two sets, x and y, which x is set of all elements of G such that the square of these elements in the center as a set x, and if the square is not in the center as set y. So the union of x and y is the whole group G, and that's the vertex set. And here we can see that, for example, if we have x in set x and y in the set y, then x is not adjacent to y, so we don't have any edge between vertices from x and y. The degree of any element in x is the order of center minus 1. The degree of any elements in y is exactly the order of center. And here is the structure of the central graph, which is the union of some complete graph, some of size of order the center, and some copies of complete bipartite graph with the same size in each part. Now, if we define the centrality degree means that the set of all pairs x and y such that x, y is in the center divided by order of G square. So we can give a relation between the number of edges of central graph and the centrality degree. So the number of edges of centrality degree is half of order of G square times the centrality degree minus the size of set x, which I defined. Here are some examples. This is for S3. If we have the centrality degree of S3 is 1 over 6. Now the number of edges is 1, as you can see here. And for dihedral group, we know that the centrality degree is 1 over 4, and the number of edges here is 4. Okay. Now the next algebraic graph is permutability degree and permutable graph. So first we define the permutability degree and then the permutable graph. I don't remember to define permutability degree in the previous lecture. Now let me just remind again. So if G is a group and if we have two subgroups H and K, we can say that two subgroups H and K are permutable if HK is equal to KH. Now, if LG is the set of all subgroups of G, now the permutability degree of G is the set of all pairs of subgroups G, so the set of all pairs H and K such that HK equal to KH divided by order of LG square. LG is the number of subgroups. So the square of the number of subgroups. For example, if you look S3, for S3 we have 6 subgroups, right? Now you can see that trivial subgroups H1 is adjacent to all other subgroups, right? So if we have a normal subgroups is permutable with all other subgroups. So here we found the permutability degree, right, which is 5 over 6. Now, as as you remember, I defined the dedekind group. Dedekind group means the subgroup which all subgroups are normal. Here are some results for the permutable group, permutability degree. If G is an abelian group, so the permutability degree is 1. If G is dedekind group, again the permutability degree is 1. So the permutability degree, we can see that is the set of all pairs H and K, such that HK is a subgroup. You know, if HK is a subgroup, is equivalent to that HK is equal to KH, right? And the permutability degree of the dihedral group of order 2 times P is 7P plus Q over P plus 3 squared. Now, you remember I gave a project number 1 in the previous lecture. Now I give project number 2, which determine the permutability degree of the dihedral group of order 2 times n. You know what you have to do if you have to consider all subgroups of the dihedral group of order 2 times n, and then you can see that each subgroups is permutable which of subgroups. You have to count all pairs and then compute the permutability degree as I computed for the dihedral group of order 2 times P. But here is for the general case. So this is the project number 2. If any of you interested, so you can deal with them and just keep in touch with me. Now, by the definition of permutability degree, we can define the permutable graph. Permutable graph means a graph associated to group G, right? The vertex set is the all subgroups, the set of all subgroups of G, and 2 subgroups H and K are adjacent if and only if HK equal to KH, which means that H and K are permutable. For S3, you can see we have 6 subgroups, so we have 6 vertices, and here you can see the graph, the permutable graph of S3, and we have 12 elements. For dihedral group of order 8, here is a graph, and here are some results about this graph. This graph is always connected. The diameter is at most 2. The girth is 3, of course, if we have a cycle. And the graph is K2 if and only if G is a cyclic group of order a prime number. There is a relation between permutability degree and permutable graph, and this is the relation, you know, that this is the relation between the number of edges and the permutability degree. And here is example. You can see the number of edges is 12, and if we use this formula by knowing the permutability degree, we will again get the 12. Now, here is some research problems. So you can find the permutable graph and permutability degree for symmetric group S4, and see that you can see that is that possible to classify all groups with with the graph, permutable graph of diameter 1. Diameter 1 means that the permutable graph is complete graph. And find some necessary and sufficient condition for the graph to be planar, and also find the graph structure for some kind of groups. For example, dihedral group of order 2 times p, 2 times p square, and so 2 times p to the n. All right, now I'm going to define two last graphs in this lecture. Graphs, algebraic graphs related to a ring. You know, if we talk about the ring, we have two operations. We have multiplication and we have addition and multiplication. With addition, a ring is an abelian group, and with multiplication, we have associativity and some more condition about distribution and so on. Now, the first graph related to a ring, and which is one of important graphs associated to a ring, is zero divisor graph. First of all, see the definition of zero divisor elements. So suppose that R is a commutative ring with identity, and element X in ring R is called zero divisor if there exists non-zero elements Y in R such that XY is 0. For example, if you look at Z4, so in Z4, you know, the element 0 is always zero divisor, because, for example, you can see that for 0 we can find 1, 0, 1 equal to 0. Now, number 1 is not zero divisor, because if we multiply 1 by each of these elements is not 0. 1 times 1 is 1, which is not 0. 1 times 2 is 2, is not 0. 1 times 3 is 3, which is not 0. You know, zero divisor, it means that we have to find at least one non-zero elements with multiplication 0. 2, element 2 is zero divisor, because 2 times 2 is 0. 3 is not zero divisor, right? So the only zero divisor of Z4 are 0 and 2. For Z12, the zero divisor is 0, 2, 3, 4, 6, 8, and 9. And you can see here, for example, 2 is zero divisor, because for 2 we have 6. 2 times 6 is 0. Now, by this definition, we can put all zero divisor element by the set Z of R. Z of R is the set of all zero divisor elements of R. And if we remove the 0 elements from the zero divisor, we may denote by Z star R. Here are some examples for the zero divisor. Right? Now I'm going to define the zero divisor graph. So the zero divisor graph for ring R, the vertex set is Z star R. Z star R is the non-zero zero divisor elements. So if we have two non-zero zero divisor element, if X and Y is in Z star R, we can say that X is adjacent to Y if and only if XY is equal to 0. Here is example for Z4. You know, for Z4, the set of zero divisor elements is 0 and 2. So we remove 0, we will have only 2, vertex 2. So that's the only one isolated vertex. For Z12, the set of 0 divisor elements, and we remove 0, so we have 2, 3, 4, 6, 8, 9, and 10. And here you can see the graph. And similarly for Z3, for Z6, for Z3, cross Z3, the direct product of two cyclic group of two rings, Z3 and Z3, direct product, and Z25, right? That's some elements. Now, one of main point is that you know the definition of integral domain. We can say that R is an integral domain if x, y is equal to 0, implies that x is 0 or y is 0. So it means that the ring R is an integral domain if it has no 0 divisor element. So if R is integral domain, so it means that in this case the vertex set is empty. We don't have any vertex. So we assume that the ring R is not integral domain in this case. Here is some results about the 0 divisor graph. So here, if A and B are two integral domain and R is the direct product or direct sum of A and B, then the graph is complete bipartite, right? And here are some examples about the 0 divisor graph, right? So for example here, if R is ZP times ZP, so the graph is complete bipartite graph KP minus 1, P minus 1. If R is Z2 cross ZP, we will have a star graph, and so on. So I asked about the product of 3 copies of ring ZP. Here are some results about the 0 divisor graph, about the about the gates, about the for example here. So it's important to see that when the graph is finite, we may have R is an infinite commutative ring, but the 0 divisor graph is finite. If R is finite or is an integral domain. Here is some upper bounds for the diameter and something about the graph when it's complete. Now the last graph associated to a ring is intersection graph of a ring. Intersection graph, we have many kinds of intersection graph. So one of important of them is intersection graph of ideals in a commutative ring. So if R is a commutative ring, so we may denote the intersection graph of ideals in ring R. We may denote by G of R. The vertex set is the set of all proper ideals and non-zero and proper ideals. And we can say that two ideals I and J are adjacent if and only the intersection is not 0. So you can see that here an example for ring Z6. We take two ideals I and J, and you can see that here we have two isolated vertices. If R is a ring of order PQ, so ZPQ, right? So we have two ideals here, and still we have two isolated vertices. Here for ZP to the 4, we have three ideals, and that's a triangle for ring ZP square Q, right? We have four ideals here, and this is the graph. And here are some more examples about intersection graph, and that's are some results about the intersection graph. For example, you can see that in this theorem that this conditions are equivalent. The graph is complete, is equivalent to that if we take two ideals I and J. If I intersection of I and J is 0, so we should have one of I and J is 0. And here is if we have the intersection of two ideals, the ideal generated by A to principal ideals is, if the intersection is 0, so A or B is 0. And we may also compare the intersection graph for ring R with the intersection graph of the ring of polynomials or polynomials with coefficient in R. And here you can see that the intersection graph over ring R is complete if and only if the intersection graph over the ring of polynomials R of X is complete. Okay, hope I introduced 11 graphs, 11 algebraic graphs in this lecture. Mostly are associated to group, but we may have many graphs associated to rings. So I just gave two of important graphs, algebraic graphs associated to rings. Now, up to now, we get some familiar with algebraic graphs, right? Now, from now on, I will focus on some graph theory tools in algebraic graphs. So, in the second part of my lecture, I will introduce some matrices associated to graph and then compute this matrix for algebraic graphs. Thank you very much. Inshallah, I will give in the next lecture about some matrices in graph and eigenvalues, and so it is some linear algebra concepts associated to graphs. Thank you very much indeed, and I'm available for any comments or question. Thank you very much indeed.
Okay. And the question is, usually when I in my experience, usually it is not always easy to find some specific properties of the whole graph. Yeah. And in this case, in my mind, when I have this problem, then I will try to consider some like some sub set of the vertex set and try to find some properties. Then from that, hopefully we can derive some properties for the whole graph. For instance, about the maybe about the planarity, or maybe or the GERD number and so on. Even it is only for the upper bound of the number, not exact number of the GERD and so on. And but I'm not sure whether it is quite good or not. So in this uh, occasion, we would like to ask your maybe like advice what we should do when we have this problem in during our research. Thank you, Professor.
Right. Thank you very much, Dr. Yani. It's a very good questions, because when we start to research for a given graph, sometimes maybe it's easy to find some graph parameters and some properties of graph, and sometimes it's so difficult. So if the problem is so difficult, for example, if you are going to find an independence number, right? So suppose that you are going to find an independence number. So for some graphs, you can determine the exact, the precise value for the independence number. But sometimes you may see that it's not easy to prove. We know that we have an independent set, but it's not easy to prove that the maximum size of independent set is this number. So in this case, if you give an upper bound or even lower bound, it's interesting. So it means that you don't need to live about independence number. So upper bound or lower bound is still interesting, you know. And sometimes we may state something which we believe that it's true, but we are not able to prove that. You may give as a conjecture, or is a problem in your paper, and that one is interesting because somebody else may continue your question and prove it, and they will just give a citation to your paper, and that one is also interesting. So it depends on the problem and on the graph, because we have many kind of graphs, and well, it's your experience that the first one you have choose the graph which you can able to find something, because if you take a graph and if it's not possible for you to find many results, so maybe you can leave this graph to another graph, right? So you have to try. So you have to try as much as you can. That one is interesting. I think this is a challenge, you know. In the recent, you have a challenge, so you have to see the problem. You have to try sometimes and do something more. And even if you are not, so you may live as a conjecture about your guess. You know, that's my opinion. but maybe Prof in the say something more about her experience in research.
Thank you very much, Professor. Yeah, I will. Thank you.
Prof Inda, you may also give us some comments.
You have already give a very good suggestion. I think it's enough. It's very good suggestion for Brienne. Okay, another question or comment maybe for. Okay, just a short question from me, Prof. Erfanian. It's about the adjacency of the product of two groups, for example, or two rings, for example. Yes. I saw from your presentation that the adjacency is point-wise, right? Adjacency to, for example, G1, product of G1 and G2, and we define the adjacency, for example, commutativity or non-commutativity, so we can define it by point-wise. Is it true?
You know, when you are talking about the product of groups, direct product of two groups, so that's the special structure for direct product, you know. So direct product of two groups is a group. Now, when we associate a graph to a given group, so if you have two groups, G1 and G2, so you will have two associated graphs, for example, gamma G1 and gamma G2, right? Now, we have some graph operations between two graphs. You know, we have Cartesian product, we have strong product, corona product, we have many products. So it's interesting to give a relation between the products of two graphs associated to group G1 and G2, right? And the graph associated to direct product of two groups. So sometimes we have equality. Equality means that the graph of direct product of two groups is, for example, Cartesian product of related to graphs. But sometimes we don't have equality. Maybe we may have the graph associated to direct product is an induced subgraph of the product of. So it depends on the situation of graph, and it's very interesting to deal with some graph operations, because if you are talking about the rings, if you are just assuming the direct sum of two rings, right? So what's the relation between graph associated to direct sum with the just a special operation of graphs related to each of the rings? So this one is one of important question for any graph, not necessarily to group, but also to ring and so on. So to give a relation between graph operation and just product of two rings or two groups. So it's very interesting, and it's not so easy because sometimes it's very difficult and we are not able to determine the exact graph structure for direct product of two graph associated to direct product of two groups or two rings and so on. So it's very interesting, and I think in the maybe in part 3 of my lecture, I will give some relations between, for example, topological index of a graph, in algebraic graph, comparing to the topological indexes of direct product of two to graphs. You know, it's a little bit complicated. Sometimes it's easy, but many times it's very difficult. But it's very interesting to deal with the graph operation and the product of two groups or rings.
Thank you. Okay, any other question?
Can I
Pak Uha
ask?
itself, you have a question?
So yeah, I'm interested in zero divisor graph and
Which graph?
zero divisor graph.
Zero divisor graph. Yeah, this is
Yeah,
number
because
10.
the idea is looks like simple, and there are some people who are trying to generalize. For example, like some people try to define clean graph of a ring or another graph of a ring, and using the motivation of zero divisor graph. So is there maybe some special tools behind it to define the new stuff based on certain thing before, or is it pure trial and error for trying to define? Yeah.
You know, as I introduced some graphs associated to groups, so we are able to define some graphs associated to a ring. But you know that if we are talking about the ring, in ring we have two operations.
Yep.
For example, if you have a group, so you have only one operation between elements in a group. But here, if you are talking about the ring and graph associated to a ring, you have two operations. So if X and Y are elements in a ring, and if X and Y are also two vertices in a graph associated to a ring, so now you can use X, Y, and X plus Y, right? So sometimes you can use the multiplication, addition, or multiplication between elements in a ring. And it's very interesting because sometimes when you are talking about, for example, the planarity, you may use these two operations to define induced subgraph isomorphic to, for example, K5 or K33. So it's very important about the ring. But I think the motivation of defining a graph associated to a ring is that you have to give a relation between ring properties and graph properties. So we have zero divisor element. So that's the definition in ring theory, right? We use this definition to define the zero divisor graph. So it means that the properties in a ring will produce a graph. Now we have many properties in graph. For example, we have in a ring, we have, for example, you know, one of important matter in ring theory is that some special ideal, for example, Jacobson graph, Jacobson ring. So Jacobson is a property. I define a graph which the name is Jacobson graph. So just give a relation between Jacobson ideal and the graph, or even for nil radical and so on. So the main point is that to give some relations between algebraic properties in a ring and graph properties to associated graph. That's very important, right? We have many graph, and also we have some generalization of the zero divisor, which you mentioned. We have many kinds of zero divisor graph, generalization of zero divisor graph, and you know, it's also important to assume that a ring is commutative or is not commutative. This is one of important thing in algebraic graph, the graph associated to ring, because if you assume that the ring is commutative, right? So you will have many things, but if you remove the commutative property in a ring, so it's very difficult. So you have to care about the commutative. Or sometimes we may have a ring with identity, and sometimes a ring maybe we don't have identity, right? So that's very important to give some relations between graph associated to ring and just algebraic properties in a ring. What I wanted to mention in this lecture today, I just want to give some some important algebraic graphs. It's not all. We have many graphs in algebraic graphs, not only for group but also for ring. And sometimes we may have some graphs associated to R major, to vector space, so to some other algebraic structure, to semi-group, to semi-ring, So it's a very wide area of defining algebraic graphs to rings. So depending on what you want to follow, is that you can deal with the algebraic properties and graph properties. So that's the point which I can just explain to you.
Yeah, I get the point. Because yeah, it is very interesting, and I saw in Google Scholar there are 1,000 papers related to zero divisor graph. So that's really, yeah. Okay, thank you very much.
Okay, I think it's enough, Pak Uha. Well, masih ada pertanyaan? Anyone? Any questions?
Yeah.
I think it's enough, Pak Uha.
Okay.
Okay.
Yeah, you can close this.
Oh, okay.
Okay.
Bu Indah yang
Apa saya?
Alright. So
ikut aja.
I think,
thank you.
yeah, thank you. We have thank you for the nice presentation. It's very interesting, and we will meet again next Saturday. I think, yeah, Saturday.
Inshallah.
Inshallah,
Yes.
it's the same time. Yeah.
In the next weeks, inshallah, I will give some relation between linear algebra and graph and algebra and probability all together.
Okay.
So it must be interesting because we combine many concepts in graph theory, in algebra, in linear algebra, and in probability. So thank you very much.
Thank you very much.
Thank you very much, Prof.
Thank you, Prof. Yuni.
Yeah. Thank you everyone. Terima kasih semuanya.
Thank you. I follow, but there is a problem out surrounding our house. So many sound. Okay.
Yes.
So,
Thank you very much indeed.
Thank you.
See you next week. Inshallah.
See you next week.
Goodbye.
Goodbye. Bye.
Goodbye.
Yeah. Bye.